Hello, college algebra students. This is Miss Quinn. I wish we were back in school. Not sure how long it's going to be before we are. This is our first video lesson. We're starting Chapter 9, Sequences and Series. I'm going to do the first video with sequences to make sure it stays short enough, and then I will pick up with series, but both are in the first lesson and for the first assignment. So we're going to use and write sequences, which a sequence is just a set of terms, meaning a set of numbers that are written in a list with commas separating each term. Use summation notation to write and find sums of series. So series are the sum of the set of terms in a sequence. Terms in a sequence are annotated by a sub something. So the first term in the sequence is annotated with an a sub 1. Oops, didn't mean to move that around. And then the fourth sequence is a sub 4. And then if you have the rule or expression that gives you any term in the sequence, for example, the nth term, so the nth term could be the 7th term, the 11th term, the 12th term, so it could be any term in the sequence. You'll normally have an expression that gives you the rule for finding any of those. So this one is a sub n equals 5 plus 7. We have some others down here that are a sub n equaling 2 to the n minus 3, a sub n equaling n squared minus 12, etc. So any of those can be rules that would find any of the numbers in the sequence. If we are given the rule for the sequence, it's pretty easy to find the terms. So if we're looking for the first 5 terms, that means we want a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. And all we have to do to find those is, again, plug in the sub number in to the rule and then calculate. So, I guess I should have written a1 right there. And then we'll write a 2 for the a sub 2, and then a 3, then negative 9 times 4, and then finally negative 9 times 5. All of these we are adding to 100. So we've got, 91, and then 82, negative 27, so that would be 73. Negative 36, so that would be 64, and then negative 45, so that would be 55. And how we would write them is horizontally, 91, comma, 82, comma, 73, and then the final 2. If we have the rule for the sequence, it's pretty easy to come up with the terms. Sometimes we're given the terms and we have to come up with the rule. So that's not quite as easy and requires us doing a little guessing and a little practicing in order to get better at it, more efficient at it. What we want to do is take a look at how the sequence is changing. So in this first one from 22 to 19, it's a minus 3, and a minus 3, and a minus 3. And a minus 3, and a minus 3. So the change in the numbers in this sequence are linear. We go down by 3 for every subsequent term. So it's kind of like slope, where we would do 19 minus 22 over the second term minus the first term, and we get negative 3. So we definitely have a linear growth model. A sub n, negative 3 is like our slope. So we could have negative 3 times our input variable. And we're getting closer to our rule. So we can try that. A sub 1 equals negative 3 times 1. But that only equals negative 3, not 22. So it's clear that our rule has, since it's linear form, like y equals mx plus b, has another y-intercept other than 0. So there is some constant that we start with, kind of like where we would start on the y-axis if we were going to graph it. So we can try a sub 1, negative 3 times 1 plus c. We know that equals 22. And then when we add 3 to both sides, we get that c is 25. So our rule is negative 3n plus 25. Now we want to make sure we check later terms, because we may find something works for the first term and then not for subsequent terms. So 1, 2, 3, 4, 5. So let's try the a sub 5 equals negative 3n plus 25. So we're going to plug in 5. And we do, in fact, get 10. So we've checked it. Our next example is not going up by a constant. So I can't add anything to negative 1/8 to get 1/4 that I can then add to 1/4 to get negative 1/8. So you can see the change in between each term is not the same. It's not just a subtracting 3 or an adding 2 or whatever. What we actually have here is what looks like exponential growth. So the denominators go 2, 4, 8, 16, 32. And so that's actually when we have 2 to some exponent. But that's our denominator. Our numerator isn't changing. So our numerator is 1 the whole way. The denominator we said was going up by powers of 2, right? So to the first power it would be 1/2, only this is negative. The second power is positive, so that's what's going to determine whether or not the negative should be on the outside of the parentheses or the inside. If we put the negative on the outside of the parentheses, then every single term should be negative. If we put it inside the parentheses, then the positive and negatives are going to alternate based on whether or not n is positive or negative, the exponent we're using. So we can just try this out. A sub 1, negative 1/2 to the first power does equal negative 1/2. Let's try a sub 6. Actually, so 1, 2, 3, 4. Actually, we don't have a sub 6, so let's do a sub 4. A sub 4 is going to be negative 1/2 to the 4th, and that does, in fact, equal 1/16. So we have the correct rule for this one. Our last one, if we look at how that changes, we go from 2 to 6, and that's a plus 4. And then we go from 6 to 12, and that's a plus 6. And then we go from 12 to 20, and that's a plus 8. And then 20 to 30 is a plus 10. So it's not linear growth. It's also not the same kind of exponential growth that we saw in the last example, right? So we went up by powers of 2, 2 to the first, 2 to the second, 2 to the third, etc. This isn't doing this. It's going up by inconsistent integers. So let's maybe see what the change of the change is between the first and third. So we have from 1 to 2, we have a change of 4. From 2 to 3, we have a change of 6. And basically the change in the two changes is just 2. So from 4 to 6 is 2. 6 to 8 is also 2. 8 to 10 is also 2. So what this is telling us is that when we have this second tier change of 2, it's not a plus 2 because it wasn't the first change like we had in our first example, but it actually means that we have something to the second power. So it's like a quadratic. So n squared plus something, because a sub 1 would be 1 squared, which is 1, not 2. A sub 2, so we have a sub 1 would be 1 squared plus something, and that equals 2. And a sub 2 equals 2 squared plus something, and that equals 6. So we have 4 here, and then 1 there, and so we're adding 1 the first time to get 2, and we're adding 2 the second time to get 6. So maybe what we're adding is just the n value. A sub n equals n squared plus n. We can check that with maybe our third term. 3 squared plus 3, that does in fact equal 12. Great. That is it for the sequences portion. I'm going to close this video now and start a new one for series so that neither of them are super long. They are both again for the same day though.